Hi everyone, welcome once again to the video lectures of E635 Applied Linear Algebra. My name is Debasattam, your instructor, and this would be the 14th and the final lecture for the fall semester 2020. We have more or less covered what we intended to. Only a little bits and pieces have been left out because of the time constraint and because of this extraordinary situation. As you can also see that things have also changed a lot. Like you can guess from my background that I have shifted to a new apartment from where I'm broadcasting this. So let us do a very quick. So this lecture is going to be much unlike the earlier lectures, right? So for this lecture, we are not going to have 3 modules. Rather, we'll have only one much smaller module. So let us just do a very quick recap of what we have done in this course from the very beginning. Yeah, so our initial part, we concentrated on how to solve equations like ax equal to b, where a is a matrix, not necessarily square. It's a m by n matrix with real number entries, and x is an unknown vector of size n, and b is a known vector of size m. Yeah, column vector. Both x and b are column vectors. Then how to solve ax equal to b. And we saw that this idea of that there is a solution if and only if rank of a and rank of a augmented b are the same. If those ranks are less than the number n, then there will be infinitely many solutions. And if those rank conditions don't match, rank conditions do not hold, the ranks don't match, then there would be no solutions. We saw that this rather technical statement has a lot of meaning physically, geometrically. What were the meanings? How those to understand those those physical meanings or geometrical meanings, we we had to develop a lot of machinery, right? Namely ideas like abstract vector spaces, then subspaces, then operators on vector spaces, linear transformations on vector spaces. Yeah, and that sort of introduced us to this abstract idea of linear algebra, where we learned about these abstract ideas together with things like fields and all, right? And once those things were done, then we moved on to the very important idea of coordinates for vector spaces. Yeah. Before that, we in fact talked about basis. Even before that, we talked about linear independence, linear combination, linear independence, span, basis, and then dimension, right? And then we talked about this idea of coordinates, and together with coordinates, we found out that finite dimensional vector spaces can always be represented by columns of numbers. Yeah, through that identification. And once that was done, we also saw that linear transformations are nothing but in coordinates. Once you represent everything in terms of coordinates in a vector space, linear transformations get represented by matrices, right? So all those ax equal to b kind of things that we were trying to solve were actually ideas originating from linear maps. Okay. With linear transformations, we got to know this immensely important theorem called the rank nullity theorem. Yeah. And so, yeah. Then afterwards, we saw that there is this idea of dual spaces, namely the space of all linear maps from the vector space to its field of scalars. And we found out that for finite dimensional cases, at least, these two vector spaces are in fact isomorphic to each other, right? With dual spaces, we also got to know about, for finite dimensional cases, corresponding to a basis for a vector space, the dual space will have a dual basis which satisfy together with the basis some of the very special properties. Yeah. Then we sort of move to special cases of real numbers and complex numbers, over which if vector space is defined, then one can also talk about something known as the inner product. And whenever there is a vector space which admits an inner product, we saw that such a space called an inner product space has all these very nice properties in terms of best approximations of vectors in by a vector, by another vector, the approximant vector in a given subspace. And with this, we actually saw various applications of this idea of inner product spaces and best approximations. We found out that best approximations is abstractly always given by that particular vector for which the error, the corresponding error, is in fact orthogonal to every vector in that subspace, right? With that, we moved on to eigenvalues and eigenvectors. We learned about invariant subspaces. We learned about how matrix representation in terms of invariant subspaces look like. Yeah. And then we understood things like diagonalization, that a matrix is diagonalizable if and only if it admits n linearly independent vectors, n linearly independent eigenvectors, where n is of course the dimension of the vector space. But then we saw that there are many situations when the matrix is not diagonalizable, or the linear operator is not diagonalizable. In that case, what we do, we saw that we can obtain a block diagonal representation, namely the Jordan canonical form, from the ideas coming from polynomial algebra. This is roughly in a nutshell what we have done, right? What we've missed out is something known as the rational canonical form, which actually is obtained by looking at what is known as cyclic subspaces, right? What are cyclic subspaces? So the idea is very simple. So think of a finite dimensional vector space and think of a vector. And let's say A is a linear operator from V to itself. Then you generate this vector space by taking the vector V, then the vector AV, A acting on V, then the vector A squared V, then the vector A cubed V. Does it look familiar? Of course, because this was there in the take-home task that you had, right? But so the idea is that if you let these guys continue forever, this thing is going to stop at some time. What do I mean by stop? You see, when I have V and AV, if V and AV are linearly dependent, then the span of VAV will be the same as span of V, right? On the other hand, suppose they're linearly independent, then VAV will be something. Then we look at A squared V and we check once again whether A squared V is linearly independent with VAV. That is, if VAV, A squared V, this set of three vectors, whether this set is linearly independent or not. Yeah. So whenever we achieve linear dependence for the first time, that means till then we had all linear independence, then it follows that there is something that you can say about the minimal polynomial of that vector corresponding to this linear dependence. Of course, we have already seen this. See, suppose I have V, A, V, A squared V up to A cube V, and then let's say A to the power 4V, I have linear dependence. Then I can say that A to the power 4V can be written as a linear combination of V, A, V, A squared V up to A cube V. Why? Because there is a linear combination that goes to 0. But then in that linear combination, the coefficient for A to the power 4V cannot be 0, because if it were, then I would have had a linear combination of V, A, V, A squared V, A cubed V that is going to 0. Yeah, non-trivial linear combination. That is absurd because I've already assumed that V, A, V, A squared V up to A cubed V, they were linearly independent. I was achieving linear dependence for the first time when I considered A to the power 4V also. Right? So therefore, A to the power 4V will have non-zero coefficient. So I can divide by the non-zero coefficient, and dividing by the non-zero coefficient, I can see that A to the power 4V can be written as a linear combination of the first four vectors, namely V, AV, A squared V, and A cubed V. But then that also means that there is a monic polynomial of degree 4, right, which when acts on V produces 0. This is the so-called minimal polynomial of the vector, and minimal polynomial of A with respect to the vector V. Yeah, is that all right? Now you see, once I have this minimal polynomial, why is this minimal polynomial? Because no smaller degree polynomial will have this property, will annihilate V. That contradicts the idea of linear independence of V, AV up to AQ. V. Now, once I have this polynomial, something funny happens. From the next step onwards, listen very carefully, from the next step onwards, we'll keep on having linear dependence. It cannot happen like I had linear independence up to some time, then I had linear dependence, and then further if I move on, I have once again linear dependence. That cannot happen. Linear independence, that cannot happen. Once there is linear dependence, it will continue for all the higher powers also. Let me tell you why. So we had this a to the power 4v expressible as a linear combination of v a v a squared v up to a cubed v, right? Now listen. This means there is this polynomial mu v s, which is such that mu v a acting on v is equal to 0. Mu subscript v, of course, I mean. Yeah. Now suppose I have a to the power 5v. I claim that a to the power 5v once again can be written as a linear combination of v, av, a squared v up to a cubed v. Why? This is why. Look at a to the power 5. Think of s to the power 5. Now divide s to the power 5 by this fourth degree polynomial, which happens to be mu vs, and divide with remainder. So suppose the remainder is rs. What can you say about the degree of rs? Of course, the degree of rs will be strictly less than the degree of mu vs, which is 4. So degree of rs is strictly less than 4, which means it could be 3, 2, 1, or 0, right? If now it is 3, 2, 1, and 0, what does that really mean? That means the following. I can write a to the power 5 as mu vs, mu va, multiplying the quotient of this division plus the remainder of this division. Yeah. Now look at what happens when I make these two operators act on v, because the two operators are the same, namely a to the power 5 is equal to mu va into qa, where q is the quotient of this division, plus ra, where r is the remainder. So a to the power 5v must be equal to mu va qav plus rav. But now look at this term, mu va qa, they commute because both of them are polynomials in a, they commute. So it's qa mu vav, but mu vav must be 0 because we've seen that this is the minimal polynomial of v. If this guy goes to 0, what we have is a to the power 5v is rav, but notice ra is a polynomial of degree 3 or less, which means it will be a linear combination of v, av, a squared b, v up to a to the power 3v, a cubed v. You see? So with this idea of long division with remainder, you can actually show that every a to the power kv is actually a linear combination of v, av up to a to the power cube v only. So depending on the degree of the minimal polynomial of a with respect to the vector v, yeah, this space that you have generated by looking at v, av, a squared v, and the span of these vectors, that dimension depends on the degree of that minimal polynomial, because every other higher power is actually a linear combination of these guys. So when we look at this space generated by v, av, a squared vs, and so on, that actually is the space generated by v, av, a to the power v, v, av, a squared v, a cube v plus dot 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 up to a to the power kv. Yeah, this has dimension k plus 1 because there are k plus 1 linearly independent vectors. Yeah, this means that the degree of the minimal polynomial of a with respect to the vector v has degree k plus 1. Yeah, is that understandable? So this subspace is called the cyclic subspace generated by V. Yeah. And with this idea of cyclic subspaces, one can actually show that if there is a matrix A and there's minimal polynomial of A, which is some polynomial, then there is always a vector which will always be able to find one vector at least for which the minimal polynomial with respect to this vector is the same as the minimal polynomial of the original operator. Yeah. And then that cyclic subspace, if you generate, that will give us a subspace which is whose dimension is equal to the degree of that minimal polynomial, right? And more importantly, this cyclic subspace then will turn out to be A invariant. Because if it's now, if it's very simple to show that it's A invariant because it's it contains all those V A squared B and so on, linear combinations of them. If you multiply by A, you get something a little higher power of A in that, but every higher power is already there, as we have seen. So such are cyclic subspaces which are A invariant, and using that idea of A invariant cyclic subspaces, one gets this idea called a rational canonical form. Yeah, and one can, what happens is you get a block which is whose minimal block whose minimal polynomial and characteristic polynomials are equal, and it will have minimal polynomial exactly equal to the minimal polynomial of the original matrix. But the original operator may have different characteristic polynomial and minimal polynomial. So based on that, we'll have further such blocks of matrices whose minimal polynomials are equal to their characteristic polynomials. Such a form is known as a rational canonical form. We just didn't have the time to cover this, but this is a fascinating story. Maybe when you guys land up here, we'll have some time to talk about these things, right? Yeah, this is what I just roughly wanted to convey. I sincerely apologize for not being able to cover this, but then, situation was difficult for all of us. So yeah, I hope you guys can forgive me for that. Okay, so now finally, I hope you did enjoy this course. Yeah, above all else, it is perhaps most important to enjoy what you are doing. Only then you get to, what should I say? You get to the depth of this, and you sort of experience the ideas to its full extent. Yeah, so enjoyment is very important for this. So I hope you did enjoy this course, and also I sincerely do hope that you have learned something from this course. And once again, I hope that you would be able to use these things in your life somewhere, yeah, in either future research or whatever job that you might land up with finally. And I'm sure that these things that you've learned, they will find use in your life, that's for guaranteed. And finally, I hope that this has caused some sort of improvement in your thought process, in your in your ability to express mathematical thoughts, your ability to think about hard mathematical problems. Yeah, so these are the qualities that we need to inculcate in ourselves in order to become a better researcher, um, perhaps perhaps even a better human being, right? So I, for one, personally did enjoy your company, although virtually, and I sincerely do hope that I wish that I could have taught you, when you guys were physically here, we could have interacted more easily, but then because of the situation, it could not happen. I hope that the situation will get back to the way things were sometime very soon, right? So that's that then. So If you have anything to tell me, then you know my email ID. So you can directly write to me personally, or if you want to share your thoughts with the whole class, you can use the Google Classroom stream, or you can comment on the YouTube videos as well. Okay, so all the best then. And by the way, I will try to upload one final problem set, but it will not be an assignment. You will not have to solve and submit, but just solve them, in order to get some idea as to what sort of questions you can expect in the INSEM exam. Yeah, I guess that's all for now. So let's meet again perhaps in the next semester. Hopefully by then things will become at least a little less abnormal, so to speak. I guess that's it. So, all right, then take care of yourselves, stay healthy. Yeah. And I would really appreciate if you guys write to me with your issues, with your feedback, with your problems, whatever. If, even, of course, if you have any problems in understanding any topic from the course, starting from the very beginning, you're very much welcome to write to me, right? Okay, then. So that's it from me. Bye bye. Take care.